Welcome to the Deep Dive. Today, in our ongoing Science Corner series, we're tackling a really interesting development in artificial intelligence. It's called Dreamer v3.
That's right. And we've got some great sources to guide us. There's the main research paper, Dreamer v3, Mastering Diverse Domains Through World Models by Hafner and his colleagues.
Yeah, and also some lively discussions from the Reinforcement Learning subreddit, Danajar Hafner's own project website, plus the ArcSIF preprints and the code on GitHub, so plenty to dig into.
Absolutely. And our goal today really is to understand what Dreamer v3 is all about. What makes it significant in AI research and why it's particularly exciting for, well, tackling really complex tasks.
Right. And for you, our listener, the intellectually curious amateur scientist type, we want to break down the key ideas clearly. Hopefully you'll have some of those satisfying aha moments without us getting too lost in the weeds, the technical jargon.
Exactly. We want to hit those key insights and implications.
Okay, so let's kick off with the core problem. What's the big challenge that Dreamer v3 is actually trying to solve here? Reading through the materials, it seems like a major hurdle in AI is making algorithms that are, well, generally capable.
That's the perfect way to frame it. Currently, reinforcement learning often requires a huge amount of task-specific tweaking.
Right, like needing a custom-built tool for every slightly different job.
Precisely. It takes significant human expertise, lots of experimentation, just to get an algorithm working well on a new problem. An algorithm great at one video game might need a total overhaul to control a robot arm, for instance.
Yeah, I see.
So Dreamer v3's ambition is to be this, well, more general-purpose algorithm, one that can achieve top performance across a really diverse set of tasks using just a single fixed set of internal settings, its hyperparameters.
Okay, so it aims to outperform even specialized methods without needing that constant retuning for every new scenario.
That's the key idea. Less human intervention, more inherent adaptability.
Got it. So more like a really capable Swiss Army knife instead of a whole workshop full of specific tools. Now, a central concept here is the world model. Can you break that down? How is that different from, say, more traditional RL?
Sure. So a lot of reinforcement learning algorithms are what we call model-free. They learn a policy, basically, a strategy for what action to take when directly from interacting with the environment. They figure out what works to get rewards, but they don't necessarily build an explicit understanding of how the environment itself functions.
Okay, so they learn reactions, not necessarily the underlying rules.
Exactly. Dreamer v3 takes a different path. It starts by learning a world model. This is like an internal simulation, the AI's own understanding of how its environment works. It tries to predict what will happen next, given the current situation and the action it takes.
Okay, so it's not just reacting. It's actively trying to predict the consequences of its actions within its own mental simulation. That makes sense. How does it actually build this model? I saw mention of 3 key neural networks working together.
Yes, that's right. There are 3 main neural network components. First, there's the world model itself, which, as we said, predicts future outcomes. Second, you have the critic. Its job is to judge the value or desirability of different situations it might encounter in those predicted futures.
Okay, so predicting what happens and judging how good that is.
Precisely. And third, there's the actor. The actor learns to choose actions that are likely to lead to those high-value situations identified by the critic, all operating within the predictions made by the world model.
Interesting. So the actor isn't just guessing. Its actions are guided by the world model's predictions and the critic's value judgments. Now, the paper describes the world model as a recurrent state space model, or RSSM. That sounds pretty technical. What's the core idea there for us?
Right, RSSM. The key thing is that it's designed to handle sequences of information, like the stream of observations an agent gets over time. It takes this raw input, maybe pixels from a screen, and compresses it into a more compact representation called a latent state.
Latent state, like a hidden summary.
Exactly. And this latent state has 2 parts. There's a deterministic part, capturing the predictable stuff like gravity makes things fall. And then there's a stochastic part, accounting for randomness or uncertainty, maybe an enemy suddenly appearing.
Okay, predictable and unpredictable elements.
Yes.
Yeah.
And the RSSM uses this latent state, plus the action taken, to predict the next latent state and also to reconstruct the original observation. This ability to both predict the future abstractly and tie it back to the concrete sensory input is what lets it build this powerful internal model.
Got it. So it's constantly trying to make sense of the environment's dynamics. Now, the paper has mentioned several key technical innovations that seem crucial for making this work so generally. The first one is simlog predictions. What's that about?
Ah, simlog. Yeah, that's quite clever. The issue is that signals in different environments, sensor readings, rewards, whatever, can have vastly different scales. You might have tiny values for fine motor control, but huge scores in a game.
Right, different ranges.
If you just try to learn using, say, standard squared error, the really large values can totally dominate the learning process, making it unstable or insensitive to smaller but still important changes. Simlog, symmetric logarithm, is a function that compresses large positive and negative values, pulling them closer together,
Okay.
while acting almost normally, almost linearly, for values close to zero. It uses the formula sign, x log 1 plus x. This stabilizes training across domains with very different signal magnitudes.
So it balances things out, letting the model pay attention to both big and small signals appropriately. Makes sense. The next one was Kale balancing in free bits. Sounds a bit more theoretical.
It is a bit more abstract, yeah. This deals with how the world model learns that stochastic or random part of the latent state we talked about.
Yeah.
When the model sees an observation, it infers what the hidden random state might be. That's the posterior belief. We want this posterior belief to be informed by the observation, but we also don't want it to stray too far from what the model expected before seeing the observation that's the prior belief. If it strays too far too easily, the model might become too complex or overfit. If it sticks too closely to the prior, it's not really learning from the new data.
Ah, a balancing act.
Exactly. The Kale divergence measures the difference between these two beliefs, prior and posterior. Kale balancing, along with this idea of free bits, essentially manages this trade-off. It allows the posterior some freedom, the free bits, to differ from the prior, based on the observation, before a penalty kicks in. This ensures the model learns meaningful information without just collapsing to its default prior guess or becoming unstable.
So encouraging learning from new data, but with some guardrails to keep it grounded and prevent it from ignoring its prior understanding completely. Okay. Then there was return normalization. Why is standardizing rewards so critical for a general agent?
Well, think about rewards. In one game, you might get +1 point frequently. In Minecraft, finding a diamond might be a huge, rare reward, maybe plus 1,000, but you get nothing for hours before that.
Drastically different scales and frequencies, yeah.
If the algorithm has a fixed way of exploring or learning based on reward size, it might explore too little when rewards are small and frequent, or get totally thrown off by a single massive reward, ignoring potentially better long-term strategies.
Right.
Return normalization tackles this. Dreamer v3 uses a neat trick. It scales down large accumulated rewards, returns, based on a running estimate of their magnitude, but it leaves small returns mostly untouched. This brings the effective scale of rewards into a more consistent range across different tasks.
So it smooths out the extreme.
Yeah, and crucially, this allows them to use a fixed setting for controlling exploration, the policy entropy regularizer across all domains, which simplifies the whole system and makes it more robust.
That seems really important for generality. Okay, the last big innovation mentioned was discrete regression for the critic using something called C-MEXP two-hot loss. That's a mouthful. What's the idea?
Haha, it is. So remember, the critic estimates the value of states. Instead of predicting a single continuous number for the value, which can also vary wildly in scale, it predicts a probability distribution over a set of predefined bins.
Bins, like categories of value?
Sort of.
Yeah.
Imagine bins representing values like 0, 1, 2, 4, 8, and so on, spaced exponentially using the inverse of simlog. That's the SimX part. The critic outputs probabilities for each bin. The final value estimate is like a weighted average based on these probabilities.
Okay, so it predicts how likely the value falls into certain ranges.
Exactly. And the two-hot part is a technical detail about how it's trained. When learning, instead of pushing probability towards just one bin, it pushes probability towards the two bins closest to the actual target value it experienced. This makes the learning more stable, less sensitive to the exact scale of the values.
And I guess predicting a distribution gives you some idea of uncertainty, too.
That's another benefit, yes. If the probabilities are spread out across many bins, the critic is effectively saying, I'm not very sure about this value. If it's concentrated on one or two bins, it's more confident. It handles different reward scales better and stabilizes the learning gradients.
Wow, okay, so these techniques, simlog, Kale balancing, return normalization, discrete regression, They all seem geared towards handling the sheer variety of signals and scales you encounter across different tasks.
That's absolutely the key takeaway. They build robustness and stability, allowing the single algorithm structure to function effectively across wildly different domains.
Right, robustness is great, but how did it actually perform? The paper tested it on a huge range of environments. What were the highlights?
The performance results are really quite impressive. Using that single fixed set of hyperparameters, no tweaking per domain, Dreamer v3 consistently outperformed algorithms that were specifically tuned by experts for those tasks.
Really? Even the tuned ones?
Yes, across over 150 tasks in 8 major domains. We're talking Atari games, where it beat mu0 in some benchmarks, complex procedural generation tasks in Progen, 3D navigation in DMLab, where it showed much better data efficiency than previous methods, plus various challenging control tasks involving simulated robots.
Wow.
In many cases, it didn't just match the state of the art, it set a new one, and perhaps tellingly, it significantly outperformed BPO, which is itself a very strong, widely used general RL algorithm across all the domains they tested.
Outperforming PPO pretty consistently is a strong statement about its generality. But I think the result that really made waves, the one people keep talking about, is Minecraft. Why is getting diamonds in Minecraft such a big deal?
Minecraft, yes. It's been this sort of benchmark challenge for AI for a long time. It's incredibly difficult for several reasons. First, rewards are extremely sparse. You basically get zero feedback until you finally achieve the goal, finding a diamond.
Nothing to guide you along the way?
Right. Second, the world is huge, open-ended, and procedurally generated, so the exploration problem is immense. Third, it requires really long-term planning. Getting a diamond isn't one action, it's a long sequence.
You need wood, then tools, then stone, better tools, iron, diamond pickaxe. It's a whole chain.
Exactly. It requires navigating this complex technology tree, discovering and crafting about 12 key items in sequence. And previous successes in Minecraft usually relied heavily on either showing the AI tons of human gameplay data,
Like the VPT model.
right, or they use carefully designed learning curricula, essentially guiding the agent step by step. Dreamer v3 did neither.
So it learned from scratch, just pixels and actions.
From scratch, it's considered the first algorithm to collect diamonds in Minecraft purely from raw pixel input with no human data and no curriculum shaping, just exploration and learning via the world model.
That's incredible. How long did it take?
The paper reports around 30 million environment steps. The researchers estimated this took about 17 days of simulated playtime on their hardware, which sounds like a lot, but considering the task's complexity, starting from pixels, it's actually seen as remarkably data efficient.
17 days for an AI to figure out the entire path from punching trees to mining diamonds. Wow. I did see some chatter on the subreddit asking if the environment was maybe simplified slightly.
Yes, there was some discussion about that.
Oh.
Some people pointed to potential minor modifications in the specific mineral environment setup used, perhaps making things like jumping a bit easier compared to some earlier versions.
Yeah.
So it's possible the exact task wasn't identical to the hardest possible vanilla Minecraft setup, but even acknowledging that, the core difficulties, the sparse reward, the long horizon, the tech tree, learning from pixels, they all remain fundamentally challenging. Getting there at all without human data or curricula is still a major milestone.
Agreed. Navigating that whole crafting sequence with zero intermediate rewards is just staggering. It speaks volumes about its exploration and planning capabilities. Now, what about scaling? Does making Dreamer v3 bigger or giving it more compute time help?
Yes, and the results there were very positive. They tested models with up to 400 million parameters. They found that larger models generally achieved higher final performance and learned faster efficient. So bigger was better, and faster too.
Pretty much. They also found that just letting the algorithm think more, doing more gradient updates on the data it collected, also reliably improved performance. This is really promising because it suggests that as computers get faster, this kind of approach could potentially scale up to tackle even more complex problems effectively.
That's a great sign for future potential. It's not hitting a wall. More resources seem to directly translate to better results. What did the ablation studies show? When they took parts away to see what broke. The ablations were illuminating. They confirmed that basically all those robustness techniques we discussed, the KL balancing, the return normalization, the discrete critic, they all contribute meaningfully to the overall performance. Though, some might be more critical for specific tasks than others.
So they all pull their weight.
They do. But maybe the most interesting finding from the ablations was how important The unsupervised part of the world model learning was the part where it just tries to predict and reconstruct its sensory input, independent of rewards.
Really? Just modeling the world was that crucial.
Apparently, yes.
Yeah.
That reconstruction loss was a major factor in Dreamer v3's success, which is kind of different from many older RL methods that focused almost entirely on learning from the reward signal. It suggests that building a good predictive understanding of the environment is intrinsically valuable.
That opens up interesting ideas like maybe pre-training these world models on just tons of video data, even without rewards.
Exactly. That's one potential future direction this points towards.
Okay, so putting it all together, how does Dreamer v3 stack up against other big AI advancements recently?
Well, it stands out for that fixed hyperparameter generality,
Mm-hmm.
unlike algorithms like PPO or SAC, which usually need tuning per task. It doesn't need expert data like, say, DeepMind's Gato.
Yeah.
And while other agents like Voyager have done cool things in Minecraft,
Right, using large language models.
yes, Voyager used an LLM and operated at a higher level using scripting APIs. Dreamer v3's achievement is learning end-to-end from pixels to diamonds using this world model approach, which is quite distinct.
So wrapping up, Dreamer v3 really feels like a significant marker on the path towards more general AI, doesn't it? Mastering such different tasks, including that huge Minecraft challenge with one setup is, well, it's remarkable.
It absolutely is. The clever ways it handles predictions, learns the world model, manages rewards seem key to its robustness and success, and the fact that it scales well with more compute power is very exciting for the future.
Yeah. This deep dive, it really gives a glimpse into how fast reinforcement learning is moving. An algorithm learning to explore, plan, and solve these complex problems without a human holding its hand. It really makes you think about where AI is headed.
Mm-hmm.
For our listeners, the curious scientists out there, Dreamer v3 is just a fantastic case study of AI moving beyond narrow tasks towards broader intelligence. Definitely check out the paper or the project site if you want the deeper technical story.
Yeah, definitely worth a look.
And it leaves us with a big question, I think. If we can build AI this general, what are the really big, challenging problems, maybe in science or engineering or elsewhere, that this kind of AI could help us tackle next? Something to ponder.